So we derived another version of the thermal wind relation, which looks like this: F0 times d zonal mean u dz, vertical shear of the geostrophic wind, is balanced by this meridional gradient of the zonal mean temperature. And we already saw that the perturbation to the thermal wind balance produces meridional velocities. Then the Coriolis force kicks in to balance the push by the eddy momentum flux, and the adiabatic cooling will balance the eddy heat flux. Okay, this is the vertical adiabatic cooling. We say cooling, it depends on the sign, but here it is northward heat transport, so it's the heating that has to be cooled. Okay, so Coriolis force Fv equals approximately equal to latitudinal divergence of the eddy momentum flux, which is what this equation is, and adiabatic cooling n squared g or r times w is approximately equal to latitudinal convergence of the eddy heat flux, which is this term. Approximate because we have made some assumptions there and dropped some terms. But if we relax this constraint of non-steady, no adiabatic, no diabatic heating, etc., then we can write the equation in a more complicated, fuller form. The adiabatic cooling term is now got eddy heat flux plus the diabatic heating and the heat dissipation. Okay, you can think of it as the eddy impact on dissipating heat. Okay, in this case, adiabatic cooling n squared g or r times w term is equal to latitudinal convergence of the heat flux, diabatic heating, and thermal dissipation. So the balance is a little bit more complicated, but it allows for other atmospheric processes to operate as well. But it's the idea is still that the thermal wind balance is a strong constraint, and the eddy fluxes that kick it away from this balance are going to be brought back with these various terms. So now we can obtain additional insight by defining a zonally averaged mass stream function, because in the zonal mean, meridional, and vertical plane, the flow is circulation is non-divergent, which allows us to define a stream function in the latitude vertical plane. Applying the average system averaging that we used in the zonal mean, we can write the equation as d zonal mean meridional velocity, the divergence of that term, and the vertical term have to add up to 0. This is the continuity equation where we have assumed some mean reference density to make life simpler, because as you know, atmosphere is highly compressible, so that assumption has to be taken in the right context. So rho 0 times zonal mean meridional is the meridional transport or circulation, which is given by the vertical gradient of the stream function that we just defined, and the vertical transport is defined by the meridional gradient of the stream function. We use the stream function here in the sense of the Stokes stream function, where we had looked at the vortex tubes in multiple regions, and then use the circulation around a region that covers these vortex tubes. So essentially Stokes theorem allows us to reduce an area integral to a line integral around this circulation contour, which is what essentially we are doing here by going from this equation to these stream function equations. Okay, so that was the figure we had seen for Stokes stream function. So we have various vortex tubes inside, and then it is related to the integral of the circulation that covers all these vortex tubes. Okay, without going back to that, which we did in, I think, chapter 2 maybe, let's move on to look at the example of the meridional transports we had seen before, meridional vertical transports we had seen before in chapter 1, I think. This is 1.4, figure 1.4. It's showing meridional wind at 500 and the 500 hectopascal vertical velocity. So you have the rising motion, convergence at lower levels in the Hadley cell, and divergence at the top. So we are talking about meridional stream functions and the relation to the vertical. So you have sinking motion here, so you have negative vertical velocities. This is the Hadley termination where you have large scale subsidence, adiabatic compression and warming, which is balanced by diabatic cooling, and then there is convergence into the tropical regions where there is the ITCZ, right? So we can combine the previous two equations, momentum equations, in this way, and get the stream function constructed using this approach. Okay, so that gives us, so what were the equations? 10.6a was the zonal momentum equation written in Eddy decomposition around the zonal mean. So you have the meridional, the Coriolis term and the Eddy momentum flux and the Eddy stress or the Eddy friction term, if you wish, and the thermodynamic equation in terms of zonal mean temperatures, adiabatic cooling, eddy momentum, eddy heat flux, diabatic heating, and the thermal dissipation. Okay, assuming again a steady state and using the thermal wind relation we had before, we can derive this elliptical equation, which basically has del y squared plus del z squared form. So n phi here, n psi is this complicated function, which is again ideal gas constant, Brent-Vesala frequency, vertical scale height, thermodynamic parameter R or Cp, diabatic heating, eddy heat flux, divergence of the eddy heat flux, thermal dissipation, and relation to the thermal wind. So this is now more complicated looking. So you have the eddy divergence of the eddy momentum flux and its gradient being related to the thermodynamic term. So you have this nice complicated looking combination of the eddy momentum and eddy heat fluxes in one equation. You need appropriate boundary conditions, so you can set stream function to vanish, which allows psi to be represented by a double Fourier series in y, meridional and vertical plane. So in that case, the zonal mean stream function, meridional transport stream function, is proportional to sine Ly times sine mz, where we are back to our L and M being the meridional and vertical wave numbers respectively. So the operator n psi here is proportional to minus psi, okay, which means when it is positive you have thermally direct circulation on the Hadley cell side, and on the other side when psi is negative you have indirect weak thermally indirect circulation, which we called the Ferrel cell. Okay, so the zonal mean stream function then is proportional to these various terms: meridional divergence of the diabatic heating, meridional gradient of the large scale eddy heat flux, second derivative, so then del square dy dz of the large scale eddy momentum flux, del dz of the turbulent drag force Fx, all zonal means, del y of the turbulent thermal dissipation term, which is Ft. You can find the more detailed derivation of this nice solution in Holton's chapter 10, I think. You can look it up and it's worth going through, but unfortunately there you cannot just read one chapter. You have to read many chapters from 6, 7, 8, 9, and 10, which if you have time you should do. It's a very nice book. Okay, for our purpose we're just going to jump a few steps and get to this, and then in the next podcast I'm going to provide the details of these terms and look at each term separately. Okay, so I hope it's clear how we are looking at the impact of eddy fluxes on the mean flow and how the perturbation or the deviation of the mean flow from the thermal wind balance is going to be brought back to equilibrium by this induced meridional circulation. VW is essentially an induced meridional circulation around the zonal thermal wind balance. So any perturbation to the zonal thermal wind balance by the eddy fluxes is going to be brought back to equilibrium by the induced meridional circulation. Okay.